Okay, so we're going to do part 3 here, which is now that we've graphed 4 of these, right? What would happen, if we're looking at y equals, we already used 5 to the x, or y equals 10 to the x, all right? Or y equals, 4/3 to the x, right? So all I'm doing is messing around. Notice all my a values so far are greater than 1. What would I expect all these graphs to look like? Well, after doing it 4 times, right, what I expect the graph, let's just go ahead and call it a to the x, what this graph will behave like, the one point that seems very consistent with everybody is everybody goes through 0, 1, right? Because anything to the 0 power, whether it's 5, 10, 4/3, a, whatever, right, anything to the 0 power is 1. And then as x goes to positive infinity in this direction, the graph's eventually going to explode, right, towards positive infinity. So our f of x's are going to positive infinity. But meanwhile, as our x's go to negative infinity, go in this direction, we notice that the graph eventually starts hugging, right, our function values get closer and closer to 0. So it behaves like a horizontal asymptote, right? So what are some of the characteristics that we see? What are some of the things that we've talked about when we're introducing to a function? Well, one of the big things we talked about is domain, right? So what values of x can we put into this function and get it output out? And it looks like it's defined for everything, right? I know I'm using some nice neat integers, but we can consider 5 to the 1/2 power, 5 to the 1/3 power, 5 to the negative 1/2 power, right? So we can do any kind of power, and just looking at the graph, again, it's always defined from 0 to positive infinity and from 0 to negative infinity. I can tell you where the graph is going to go, and I can evaluate it, relatively easy. So the domain's everything. Another thing that we talked about with regard to functions is range. So now that we know what I can put into it, what seems to be the corresponding outputs? And in this case, it's a limited limited range, because we're definitely going to positive infinity, and it looks like we're approaching 0 without ever crossing it, right? So we just get all our fractions just get smaller and smaller and smaller and smaller, and get closer and closer to 0 without ever really crossing the x-axis. All right, so there's our domain and range. Some other things that we have talked about, right, is we've talked about intercepts, all right? And so we can see that this function, right, no matter what the a value is, right, the function always has a y-intercept at 0, 1. And as far as x-intercept is concerned, since we're just approaching the x-axis, right, it doesn't have, right, any x-intercepts at all. It's never going to cross the graph. Okay, so we got that. In terms of end behavior, we've taken a look at that. When x is going to positive infinity, our function goes to positive infinity. And when x goes to negative infinity, our function goes to 0. So it behaves like we have a horizontal asymptote, right, of the x-axis, right? I think that's y equals to 0 in the negative direction, right? And that's quite different, because when we studied horizontal asymptotes before, right, that was occurring in both directions for both x and y. But what's kind of interesting about our exponential function is it seems to be, well, it is behaving as a horizontal asymptote in only one direction, that being the negative side. Some other things that we talked about is increasing and decreasing. This function, again, to answer that question, we're going to move left to right. And so it's, we're steadily, the growth is very small, but then at some point the growth gets to be very big. And so this function is basically increasing throughout its whole entire domain, from negative infinity to infinity. It's pretty much always on the way up. Even down here, that on the way up is very small, it's very shallow, but as we've seen, right, there's a difference between a fraction of 1/4 and 1/2. Right, 1/4 is less than 1/2. So we're steadily building bigger and bigger and bigger, right? 1/8 is, and then 1/16. All right, so the fractions are getting smaller, but that also means as we move left to right, we're slowly, slowly building until we, boom, we just take off. Again, that's why we call this exponential growth. An exponential growth curve, something happens very slowly to start, and then it explodes. And I'll talk more about that in a moment. Right? So it's increasing. Since the function's always increasing, this now means, right, another thing that we talked about is that there's no extrema. Right? There's no extrema at all. There's no local and there's no absolute extrema. Locals are where we hit hills and valleys, right? Absolute are the highest value for anything. And 0 is not an absolute minimum here because we never assume the value of 0, right? That's what has to happen for an absolute extrema. I have to assume that value, but here we are never actually equal to 0. We just get closer and closer to it. So we're always increasing, which means we have no extrema, right? No local or absolute maximums, all right? And I'm trying to think what else when we're talking about a function. We talked end behavior, we've talked about increasing, decreasing. Is it even or odd, right? And so this one, right, is neither even or odd, right? Because it has no symmetry. To be even, it has to be symmetric with the y-axis. It doesn't happen. To be odd, it has to go through a double flip and be symmetric about the origin. It doesn't happen. So this doesn't have any symmetries that would make it an even or an odd function. And I think I'm going to try to go through that. Domain range is the big one. Intercepts is another big one. End behavior, increasing, no extrema, neither. Yeah, I think those are when we were talking about all our other functions, right? Polynomial or whatnot, right? All our basic functions, those were all the things that we talked about, right? What their domains, their range, their intercepts, all that other good stuff. So there is a big analysis of our exponential growth model, right? That is how it's always going to behave. Right, and these are the characteristics of it. And one other thing I'll say, we'll get into applications later in our class, but in terms of an application, these are really good for population growth models, even though I'll talk more about that. There's some nuance in that, because this is how populations behave. If I don't have a lot of people in my population, the growth rate is relatively small. But as our population continues to grow, right, as more and more we're all adults here, right? So as more reproduction occurs, right, if there's more chances, if I have a bigger population, I have more chances for reproduction. And so what ends up happening is as my population grows, right, so slowly what starts to happen is my population begins to explode. And that's a classic behavior population. Same thing with kind of thinking in terms of a virus right now, right? The way that a virus or a rumor spreads is the same way. It maybe starts with one person, and then the growth rate's relatively slow, but at some point it starts to explode. All right, and so and then we have pandemics like we have now, or whatever the case might be. Again, there's more to that story, but you can kind of get that. And then really for you guys, this model is really famous for money, right? The classic idea that it takes money to make money basically comes in this, because if I have a little money, then I'm not going to grow a whole bunch in terms of my monetary value. But if my principal continues to increase, eventually, right, my money just grows and grows and grows, and pretty soon it starts behaving exponentially. And so that's why a lot of people, I don't know if your parents have told you or if you've watched movies or whatever the case might be, right, if you're a relatively young person, you want to start investing money now, because it'll slowly grow on you. It doesn't seem like to have an effect for you at the moment because it grows very slowly. But as your principal continues to grow and grow and grow, we call this continuous compounded interest, your money eventually starts to explode. And that's when it starts to work for me, right? And which is why some people can retire, right? And, kind of live off their retirement because they're just constantly living off their interest. But anyways, all right, so those are some applications we will see. We'll talk about population dynamics, spreads of viruses, and money, right, later on. But for now, what we're going to do is just focus on the basic behavior, talk about it, and like we've done with all our functions, once we understand the basic behavior, we can start transforming them, right? Moving them left, moving them right, shifting them, making them longer, making them shorter, all that good stuff. But we'll do that momentarily because we have another, right? This is just the growth model. Now we got to go investigate the decay model. So we'll do that in a video coming soon.